Before this section, you knew two ways to solve quadratic equations. What are the two methods that you know to solve a quadratic? Okay, so you have the right idea with vertex, but like graphing, right? So if I gave you the equation, you could graph it into the calculator and find where it crossed the. Did that one day? Okay, so we did it graphically. What was the other way?
Factoring.
It was related. Factoring, okay? So second one was factoring, which included a box method, okay? So, and then on Monday you learned, or relearned, completing the square, okay? So another method I'm going to show you now is the square root method, and then the quadratic formula, okay? So I'm just going to kind of go through these examples for the square root method. Okay, the square root method is kind of a unique method because it only works in certain situations. Okay, so all of these examples can be used, can use the square root method in order to solve them. What is different about these equations versus maybe ones that you've seen in the past?
The b value.
Right, the b value, exactly. Okay, so do you notice like 3 through 8 has no b value? Okay, so all you do is you like just solve it algebraically, okay, which is going to involve taking a square root. Okay, so for question number 3, if I have x squared equaling 9, what would my first and only step be? Square rooting, right? So if you're solving for the square root, you square root, and the square root of 9 is plus or minus 3. Okay, so if you look at question number 6, which is just slightly more complicated, what would you do for question number 6? So yeah, you start by adding 400, right? So you end up with x squared is equal to 400, and then what's your second step? Square root it. Okay, so what's the square root of 400? 20.
Oh, what do you know?
Yeah, right? A perfect break. Square root of 20, so it would be plus or minus 20. So you're still getting two solutions, just like you did on all of those other scenarios. Do realize that. Okay, now number 9 is slightly different. This kind of is like that, the step on quadratic formula. No, sorry. On completing the square. There it is. Okay, so it's like that second to last step there. So what would I do for question number 9? Square root. So then I get x minus 6 is equal to, what is the square root of 144? 12. So technically it's like plus or minus 12. So then what would I do from there? Add 6. Right? So I can say 12 plus 6, which is 18. And then negative 12 plus 6, which is negative 6. Okay, so getting two very different solutions. Okay. So 12 would be the same kind of scenario. Okay. So square root method is pretty easy. Okay. Do I need to keep going with that method? That's pretty simple. Okay. Complete. You guys did that on your own. Good work. Okay, the other method is quadratic formula. Okay, now I think that this is probably not a new equation to you. Okay, quadratic formula is something that comes back over and over, and even when you get into like bar calculus, you still have to be able to solve quadratics, and often you end up using the quadratic formula. Okay, so one thing you need to know is when can you use each of the methods? Okay, can you always use graphing? Not always. Okay, because sometimes a parabola does not intersect the x-axis. Okay, or maybe it intersects at like the square root of 5, which is not a nice number and we don't like to round. Okay, and then we did factoring. Can you always factor? No, factoring only sometimes works. And then we did completing the square. Can you always complete the square? You can always complete the square. Okay, You can always complete the square, but sometimes it turns into some super nasty decimals and fractions. I shouldn't say decimals, let's go with fractions. So maybe at that point, quadratic formula is a little bit easier to use. Okay, so quadratic formula and completing the square are two methods that always work, and you always get exact answers with. Okay, it just depends on the equation. One might be easier to use than the other. Okay, so everybody wrote that down and highlighted it and circled it and then tattooed it on their arms? Oh, maybe later. Okay. So let's do an example. Let's just steal one of these. Let's go over here. So example, we got 3x squared. What was it? Plus 2. Okay. So the first thing that you notice is what is the set equal to? 0. Okay. You can only do the quadratic formula if it's set equal to 0. Okay. And that kind of holds true for all quadratics except for the first step on completing the square. Anyway, okay, so here we go. Quadratic formula goes negative b. What's my negative b value in this equation? Okay, so negative 7 b squared. Ooh, okay, now if you went straight to 49, totally fine. Actually, I kind of like that better. Minus 4 times the a value. What's my a value? C value? Times 2. Okay. Yep, you're ahead of me. 2 times, and then 2 times 3 is, yep, okay. So, now how do I simplify this? Where must I start? Inside that radical, right? Okay, so as you said, 49, 7 squared is 49, and then 4 times 3 is 12, 12 times 2 is 24. And what's 49 minus 24? Well, that's awfully nice. Okay, and the square root of 25 is a beautiful 5. So we have negative 7 plus or minus 5. Okay, so now we have to split this and get our two different solutions. Okay, we have negative 7 plus 5, which is negative 2. And what's negative 2 divided by 6? Negative 1/3. Very good. Okay. And then if we do the minus version, what's negative 7 minus 5? And negative 12 over 6? Negative 2. Okay, so we are still getting those two solutions. Okay, so we could graph this and find those solutions. We could factor this and find those two solutions. We could complete the square and find those exact solutions. Or we could quadratic formula that sucker. Okay. Do I need to do another example of, I'm going to make one up, because I want one to be kind of a little nasty. And when I make stuff up, that's usually what happens. I want it to like not be a perfect break is what I mean, just so you can see the difference. So let's say we had 3x squared minus 5x plus 8. That shouldn't be too nasty, and I don't think it's factorable. Oh, maybe it is. Hold on, let me change that. Sorry. Let me change the 8 to about a 7. Okay. So, quadratic formula, what's my negative b value?
5.
So, 5 plus or minus b squared. 5. So, is everybody okay with making sure that you don't say negative 5 squared? Let's just say 5 squared. Because I can't tell you how many people will type negative 5 squared in the calculator, and it will pop out negative 25, and they'll say, oh, it's negative 25. Please don't be that person. Remember, anytime you square a number, it's positive. Okay? So we'll just kill the negative altogether. That way you don't do that. So 5 squared minus 4 times the a, which is 3, times the c, which is 7, all over 2 times the a. Everybody get the plug part? Okay, let's do the chug. Okay, so I'm working inside the radical. What's 5 squared? 25. And 4 times 3, 12 times 7. Uh-oh. Dang it. I got too complicated. Okay, ready? I'm going to change this really slightly. My bad. I'm going to make it a minus 7. Just a minor. Okay. Yeah, because if it's a... Yeah, I don't want imaginary yet. I'm going to talk about imaginary solutions. Not yet. We're going to talk about imaginaries, but not at this exact moment. Okay, so what's 12 times 7?
7.
Yeah, 84. There we go. Sorry about my... See what happens? Told you it'd be nasty. Okay, now it's 25 plus 84.
109.
Square root of 109. Okay, so now I would check to see if 109 is breakable. Okay, so is there a perfect square number that multiplies to 109? No. Okay, so all I have to do at this point is now leave this. Okay, and that is technically 2 solutions that are exact. Okay. Okay, so check on quadratic formula. Sorta, kinda, yeah. Feel decent? Okay. And it can get a little nastier. Maybe it will. We'll get there. We'll get to the nasty quadratic formula eventually. It'll be super fun. Okay. 0, 5. Okay, so I'm calling 0, 5 complex numbers. Now, why on earth would I include complex numbers with quadratic equations? Oh, I surely do like you. Okay, so first of all, does anybody know what a complex number is? They are super complex.
Exactly.
Yeah, so like, okay, this is kind of like Venn diagram, which is kind of interesting. So this is where they introduce this brand new number to you. And it is kind of hard to fathom because it is, in fact, an imaginary number. Okay, so they call this imaginary number I. Okay, they're not super creative. Okay, and so I is going to represent what number? The square root of -1. So if you didn't know that, write this down. Okay, I is the square root of -1. Okay, so we're now giving this ability to take the square root of a negative number, okay, which is really super important. Okay, so we have these real numbers, okay, which are all the numbers that you can comprehend in your mind. And now we have these imaginary numbers, which are all the numbers you cannot comprehend in your mind. And if you add them together, it creates a complex number. Okay, so the standard form of a complex number looks like this. A plus BI. Okay, so A is like your real number, and the BI is like how many imaginary numbers you have. Okay, so we have this real meets imaginary number. Very super cool. Okay, so the first thing we're going to do is we're just going to play with some i's, and then I'm going to show you why I threw I in here in the first place. Okay, so we need to be able to identify, first of all, what part is real and what part is imaginary. So if, for example, we happen to have the complex number 9 plus 5i, what is the real number? 9. Okay, so 9 is the real, and what's the imaginary number? 5i. Okay, what about this one right here, -7i? What is the real number? 0. Okay, 0 plus -7i. 0 is the real, so what's my I? -7i, my imaginary piece, okay? So that's just identifying your terms. Very simple. Okay, now, what happens if they ask us to add or subtract a complex number. Okay, guess what you do? It's very simple. You just combine like terms. Okay, it is just like playing with an x. It's like a variable. Okay, so let's do this example. Okay, so let's say they ask us to subtract these two complex numbers. Okay, so 17 minus 6i, and we're going to subtract 9 plus 10i. How many reals do I end up with? Okay, so what is 17 minus 9? Is 8. Okay, so I end up with 8 as my real. What is my imaginary value? 4i? Negative 4. No. Negative 16? Ah, okay. So really careful when subtracting. Remember that if I have a minus in front of anything that's in parentheses, I have to distribute that negative through, and I'm technically subtracting the 10i. So what is negative 6i minus 10i? Yeah, negative 16i. Don't make those negative mistakes. Be very careful. I can almost guarantee someone in here is going to do it. Don't let it be you. Okay, another quick example, number 8. How many reals do I have? Okay, so 16 plus negative 8 makes 8. What's my imaginary value? Is what? 5i. Good. Okay, so adding and subtracting is very simple. Okay, multiplying. Multiplying gets a little more fun. Okay. Okay, so technically we're multiplying two binomials together. So when I say binomials, what am I saying? Two terms, right? So I have two quantities that have two terms. So anytime you have two binomials that are being multiplied by each other, what do you have to do? FOIL. Okay, it is no different if you have an I there versus an X. Okay, oh, you are so, oh, good. Okay. So FOILing, 6 times 3 is 18. 6 times negative 10, pi, negative 60i. Negative 5i times 3, 15i, whoops, there we go. And negative 5i times negative 10i. 50i squared, right? Because you multiplied I times I, which makes an I squared. Okay, now let's think about this. I think I can hear you guys like thinking out loud. Okay, so you were like, oh, well, wait a second, I squared, isn't that something? Okay, so I is the square root of negative 1, right? Okay, so if we square a square root, what happens? They like kill each other out, and you're left with, yeah, negative 1. Okay, so now we know that I squared is actually the value of negative 1. Okay, so if I have on my last term 50 times negative 1, what's my last term really saying? Negative 50. So really this last term is like minus 50. Okay, which now I can combine like terms. So how many reals do I end up with? Negative 32. And how many imaginaries? Negative 75 i's. That make sense?
Wow.
Okay. Should I do another example? One more? Okay. Okay, there's my example, number 11. Okay, so again, we're just going to FOIL this just like any other set of binomials. 8 times 11 makes 88. And 8 times I makes 8 i's. And, 15 i's times 11 is,
It's Alex.
yeah, 165 i's. Okay, and 15i times I.
15i squared.
Okay, so can we jump and say we get 15i squared, so therefore we just are going to say it's minus 15. Is everybody okay with me jumping that step?
Yes.
Minus
165.
165.
Oh, where did I get a 2? That's why you guys were all yelling at me. Thought you were getting excited about the minus 15. Okay, so now if I combine my constant terms, I get how many reals? What is that? 73, and then 8i plus 165 is 3i. Not bad? Okay. So, working with i's, not bad. Pretty simple. So, I'm going to actually go ahead and skip this example. It's kind of an interesting thing, and so here is the answer to the question, well, when would I ever use an I in the real world? An imaginary number in the real world. Well, if you turn out to be an electrician, they use I's with currents. Okay, so if you want to look at this, it is kind of interesting talking about voltage and ohms. But they do use I's to talk about all that stuff, and it's kind of cool. Okay, so here we go. Why do we care?
Why do we care?
We need to be able to solve quadratic equations, okay, and eventually all equations, okay? So if I'm dealing with a quadratic equation, I have x squared, blah, 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 then how many solutions should I have? 2. 2 solutions, no matter what. Okay, that means I can possibly have 2 real solutions. I could have 1 real solution and 1 imaginary solution. Or I could have 2 imaginary solutions. Okay, so I want to talk about when those scenarios exist. Okay, and I'm going to show you graphically. Okay, so remember when we were solving by graphing? Okay, and let's say we're going to take this first equation right here, and we're going to solve it. Okay, so we took our calculators out, and we typed them into our y equals. I'm going to use Desmos, if that's okay with you guys, because I love Desmos. It just takes like 10 minutes to load. We'll just wait for it. Okay, so the equation was 2x squared plus 4x plus 1. Loading. Great things take time. So, okay, so what are we going to be looking for, by the way? Where are our solutions going to be? On the x-axis, okay? So we're looking at where this parabola is going to cross the x-axis, and it's still loading. Come on. There we go. Whew. Okay, so we had 2x squared plus 4x plus 1. Okay. Come on, Desmos. Why is it not working?
You didn't put equals.
No, I shouldn't have to. Huh. Well, what? Dang it. Okay. When Desmos doesn't work, I guess you just have to use Webbit. That's weird, it worked the last period. I don't know what's going on. It's probably like overloading my little baby tablet information. It's too much. Oh, come on. Okay, let's do this. I'm going to pull this up on my... There we go. Okay. Okay, so we got 2x squared plus 4x plus 1. Yay. Okay, so how many times did it cross the x-axis? Twice. And it happened to be exactly at some irrational number and another irrational number. So this one would not be solvable by factoring. You would have to use the quadratic formula or completing the square. It would have a radical involved. Okay. Now, what if we change this to 2x squared plus 4x plus 2? Where does it cross the x-axis? One time. Okay, this is a scenario where the vertex lies right on the x-axis. So how many solutions does it have? One. Okay, now technically I could say, well, actually there's two. They just happen to be the exact same one. Okay, so this actually has a solution of -1 and -1. Okay, now do I have to list them twice? Technically no. Okay, but understand that it is technically twice. Okay, now what if I get a little fancier and I add 3 on the end of this instead? Okay, where does that cross the x-axis? It does not. Okay, so this is the scenario where we get into imaginary solutions. I cannot visually see where this crosses the x-axis, but there is a value for x that I can put into this equation and solve, and it's going to have an I in it. Does that make sense? Okay, so let's solve this one. So let me go back to, this. So let's do this. So we have example 1. Sure. 2x squared plus 4x plus 3. Okay. What method do you want to use to solve this? Give me a method. Oh, sorry. I got this. Sorry. I was writing, you guys couldn't see. There we go. How would you solve this? Give me a method. Quadratic formula? Or I could complete the square. Those are your two options. That's all you got. Okay, so pick one of those. Quadratic formula or completing the square. Okay, quadratic formula. You're looking at me like I should tell you. Okay, so it goes -b plus or minus the square root of b squared minus 4 times the a times the c all over 2 times the a. Everybody okay with the plug? Plugging it in. Okay, so now we're going to work on the inside. So 4 squared is 16. 4 minus 2 is 8. 8 times 3 is 24. So we get minus 24. All divided by the 4. So on the inside, what's 16 minus 4? I mean 24. Sorry. 16 minus 24. -8. So I get a square root of -8. Okay. Can I break the square root of -8? Okay. So the way you should be thinking is, I'm going to break an 8, right? So what two square numbers multiply to 8? 2 and 4. And the square root of 4 is 2. So everybody's okay that the square root of 8 would break into 2 square roots of 2? Okay. Now what do I do with the negative in there? What's that? Yeah, it turns into your imaginary. So it becomes 2i square roots of 2. So that square root of 1 is pulled out into the value of I. Okay, and my last step here is, can I divide each of those numbers on the outside by something? By 2. Good, so this is going to become -2 plus or minus I square roots of 2 all over 2. And notice you can't touch the radical. Things on the inside can't play with things on the outside. Outsides can play together, insides can play together. Okay, so here is your imaginary solution, which is the answer to that quadratic equation. Pretty cool? Okay, so this is super awesome. Once we get into even higher polynomials, like once we get into like x to the 6th power, guess how many solutions you get to find with x to the 6th power? 6. And if you become an engineer, you get to solve like super complicated ones using computers.
Yay.